today's topic should be pretty straightforward because we're just reviewing the unit that we've had so far on exponential functions in preparation for our quiz this week. So we're going to start off just by looking at the difference between exponential growth and linear growth. So what you need to know about exponential growth versus linear growth is that while linear growth shows a common difference, so as the numbers go up, they increase by the same amount every time, exponential growth shows a common ratio. As the numbers go up, they're multiplied by the same number every time. So the common difference is a number added. And then when it comes to exponential growth, we have a common ratio, which will be multiplied. This means that if we were to look at, for example, salary, we could say that that was an example of linear growth because every year or every hour or every day, you're paid the same amount. So you're just adding the same amount of money during every time period. If you make $15 an hour, that's linear growth. The common difference is $15. Another example of linear growth is distance traveled over time if you're going the same speed the whole time. So if you're going 60 miles per hour after 1 hour, you've gone 60 miles. After 2, 120. After 3, 180. And you're just adding 60 every time. Some examples of exponential growth are an investment might grow by a percentage every year. Growing by percentage is just multiplying by the same number every year or every month or however often. Another example is population growth. You'll often see bacteria populations that grow exponentially. So maybe after an hour, you have 100 bacteria. After 2 hours, you have 200. After 3 hours, you have 400. Because it's doubling every time. We're multiplying by a common ratio of 2. Like I said before, sometimes those common ratios are expressed as percentages. In your first bullet point here, you can write the common ratio can be expressed as a percentage. And then in the second bullet point, in order to use the percentage in an equation, we have to convert it into a decimal. And that's what we're going to do right here. So 3%, let me use a better marker than this. 3% is the same thing as 0.03 when we convert it to a decimal. In order to go from percentage to decimal, you just move the decimal over twice. This is how much it's growing by each time. But in growth situations, we add that decimal to the number 1. You can write that in your exponential growth box under percentages in exponential growth and decay. This allows us to have a number that we can multiply to our original amount and then multiply it by it again and again and again. And because we have that 1 in there, it keeps our original amount. It kind of fixes it in place. That's that like 100%. So say for instance, I had $2,000 growing at a 3% rate. Well, after the first year, I'd have to multiply by 1.03 to find out what I would have in the second year. I couldn't just multiply by 0.03 because this would give me a really small number. It would only tell me how much more I had the next year. It wouldn't tell me how much I had in total. This is the number that will do that. If something were shrinking by 3%, so this is exponential decay, we would again convert it into a decimal. And then we would subtract it from 1. Instead of adding it to 1, we're going to subtract it from 1, and that would leave us with 0.97. That would be our common ratio. If we only, again, just use the percentage instead of subtracting it from 1, that would tell us how much each year it was going down by, but it wouldn't tell us how much we actually had after each year, after it decayed by 3% every year. Okay. Because this is just a review, I'm going to keep moving. We're going to now look at the general form of exponential functions. I've got my notes down here. So the general form of an exponential equation is a format where we see each of these components put all together, an original amount, a growth ratio, and then added to all that an exponent. And what the exponent is doing in there is it's representing this sense of repeated multiplication. I mentioned in the beginning of this video that exponential growth has a common ratio, which is a number you keep multiplying by. In order to represent this in math, in order to represent something that keeps being multiplied, we use exponents. So the general form looks like this, and I'm going to write it in function notation here. So f of x, you can also think of that as y, is equal to a times r raised to the t power. This goes in the equation box. Let's talk about what each of these things mean. Okay, a is the original amount. This is what you start with. In the very beginning, you only have this. R is the common ratio, right? After 1 year, we would just multiply by the common ratio once, after 2 years twice, after 3 years 3 times, and that's what t is representing. T is the number of time periods that have passed, usually the number of years. We're going to see years most often, sometimes days. However, the problem is defining time period. So I'm going to just write, just in general, it's the number of time periods. That's because in every time period, or in every step we take, we multiply by the common ratio. All right, so according to the order of operations, we first will perform the operation of exponents or powers, and then we'll do multiplication. So if we had f of 3, and you guys might remember or might not remember, but in function notation, when we're plugging in a number, we plug it in where the x used to be in f of x, just to say when we take the function of 3. So if f of 3 is 1000 times 0.5 raised to the third power, what this means is that a principal amount or an original amount of 1000 is undergoing exponential decay, right? Because that's less than 1. And it's been undergoing that exponential decay for 3 time periods, maybe 3 years, maybe every year this original 1000 got cut in half. You can see by that common ratio what I mean when I say cut in half, right? This is half of the original. So in order to evaluate this, we are not going to just go left to right. That would be incorrect according to our order of operations. What we are going to do is actually raise this to the third power first. You're going to want a calculator here unless you're very good with decimals and mental math, which I am, so I'm not going to use the calculator. Okay, so if we raise 0.5 to the third power, this will give us 0.125. Once we have that value, we can do our multiplication. 1000 times 0.125. That will leave us with a final answer of 125. So after 3 years, our principal amount has decayed to 125. That's all that means. As you can see, we're always going to have these 2 steps when evaluating any exponential function. So number 1 step is the exponent. Number 2 is multiplication. Really, really straightforward. So when you're doing a word problem, first you've got to actually write yourself that equation that you can evaluate, which means that it's important to identify the 3 components that we're going to need for our equation. So this problem says, Andy has bought $2,000 worth of savings bonds, which will grow at a yearly interest rate of 3% for the next 40 years. What will the saving bonds be worth when they reach their maximum value? So when they hit that 40-year mark, how much will they be worth? Let's go through each of the things that we need. We need an original amount. I mean, just reading this problem, you should kind of be yelling at the screen right now. It's 2,000. It's actually how much he just invested in these savings bonds. So original amount is 2,000. Okay, let's talk about our common ratio. So we know common ratios can be expressed as percentages. So our percentage is 3%, which means our common ratio, because this is growth, is going to be 1 plus 3% as a decimal, 0.03, or 1.03. That's the common ratio. Finally, what's the time? How many time periods have passed? Well, 40 years, right? So our time is going to equal, let me use a colon, 40 years. Putting this all together, we will have 2,000 times the common ratio, 1.03, raised to the 40th power. We have 1.03 raised to the 40th power. Gives us a large number. I'm going to write it out so you can see. So I've done my exponent. We get 2,000 times 1.03 to the 40th power, which is 3.262. And then there's more, but I'm going to just round it to that number. And then I'm going to do my multiplication. So times 2,000. And that will give me 6,524.08. Now I've rounded it to 2 decimal places because it's money. And with money, you can't have any more than 2 decimal places because we got cents and nothing past that. So that's it. Okay, make sure you get your notes down. I will be checking them.